First of all, thank you everybody for your hard work over the weekend. We think that all of the projects have gotten off to a really good start. Like I was just saying, for those who weren't quite in the room yet, we've been very impressed with the breadth of project topics and with the success of each of those topics. So we think that it's been a pretty good hackathon this year overall. Like I was mentioning, we're going to go ahead and do kind of final summaries for each of your projects, and then we'll stick around for a while afterwards to give people a little bit of extra time, because I know a couple of groups were kind of getting close to having things in a state where they were ready to take a break. We don't want to cut you off just yet, but we do need to give people in different time zones a chance to present while they still can. So just as a quick summary, you don't necessarily have to cover all of these items, but some things to think about for your final summary. Again, what were your goals today? Did those change as you worked on your model? How did the progress you made today live up to those goals, and what still needs to be done with the model as of today? If you could also give us like a quick 1-minute recap of the biological phenomenon that you're simulating, that would be helpful too. And then just, you can wrap that into the discussion of how far you got in actually simulating that. You can be showing us a model of your simulation running through screen share as you're doing that. And one other thing we do want you to touch on is what were your chief obstacles in the process of getting your simulation set up and coded. You can maybe talk about 2 notable things that you think are worth sharing with the group for future reference for other projects. That's always super helpful to hear from other teams, either for catharsis because they find out they face the same problem, or for learning's sake because you can maybe learn from them and gain some wisdom so you don't have to make the same mistake in the future. Yeah, so I think probably easiest just to go through our order here. So TB or not TB, would you be okay with going first here?
Yeah, don't mind going first. Yeah, if I'm honest, I don't think we have anything that we can really show much on CompuCell at this point, but I think, like you said, we're one of the groups that's hopefully, given another hour, we might have something that runs fully as we hoped it would at the start of the weekend. So yeah, I guess to summarize, the model that we've been trying to make this weekend was one that captures the within host infection dynamics of tuberculosis. So it's caused by a bacterium known as Mycobacterium tuberculosis. Typically it gets inhaled and goes into the lungs, and then you tend to have one of 2 outcomes. Most of the time it's contained within a granuloma, so a load of immune cells surround it, wall it in, and prevent it from replicating any further or spreading and causing more damage. And about 10% of the time it spreads uncontrollably and you wind up getting very ill from it, and without a lot of antibiotics you can die from it. So our chief goal was to try and get, because there's multiple different types of immune cells that attack the bacteria. The bacteria, there tends to be, some of them can enter a sort of a less metabolically active state, so we wanted to capture the difference between fast growing and slow growing bacteria. And all in all, we just wanted all these different immune cell types and the bacteria interacting in all the different ways that the original model that we were looking to replicate does, and see if we could see some outcomes like they got, such as an example of perhaps where a granuloma does form and it all stays self-contained, or a situation where it grew out of control and clearly would have needed some antibiotic treatment. So yesterday was mostly spent writing up a load of the pseudocode, and today's been largely implementing it. And thankfully, thanks to a lot of help from the organisers, especially Pedro and James, I know have helped us a lot, so we really appreciate that. We're almost at the point where almost all the pseudocode has been turned into real code. So we're almost at the point where we could hopefully run the full model, and perhaps by the end of this evening see one full run through. There's a chance it won't be very interesting and the bacteria dies, but at least we'll be able to see it run. So yeah, I guess in terms of obstacles, one of the difficulties I suppose we had was trying to take what was a cellular automata model and turn it into something that runs in CompuCell. So for example, the bacteria dividing up, we were thinking in terms of creating a new bacterium in an empty grid space next to it, when ultimately it made more sense to have it just grow in volume, and then depending on how much pressure was on it, give it the ability to then keep growing and eventually divide into more bacteria. So that was a change that we've had to make late in the day, but has meant that we now have the replication process sorted out. So and yeah, another one, I think we found that writing things out lots of long blocks of code, if it's getting to the point where writing 50 lines of code for a process, is probably a good chance we've overlooked a much simpler way of doing it. And yeah, I guess having had a chance to actually try and make something on CompuCell allowed us to figure out, I guess, better how we'd approach these problems going forward. So yeah, I guess in general, a good hint is if you're writing lots of codes, perhaps think if there's an easy way of doing it, or a code snippet that could do it for you. So in terms of finishing off the model, I think there's just a few more processes we need to sort out. I think we're pretty close at this point. And then the hope would be this model could maybe validate the original model that we were looking to replicate, and then that could go towards a paper that I could use towards my PhD thesis, hopefully. So big thanks to Jakob and Vasileios, who've been in my team, and to all the organisers who've helped me, because if that does wind up happening, that'd be fantastic.
Great. So is there something, did you have something in a state that it does run that you might want to screen share?
I guess we could show how it looks in terms of we've got the blood vessels. Sorry, I just realized I'm not sharing screen.
I think I have to stop first. Sorry about that.
Sorry. Okay. So we've got the this is how we have the blood vessels initially randomly placed throughout this grid, and I think it's been pointed out to us that 1,000 by 1,000 grid may have been too big, and we perhaps should have looked at a smaller scale to start with. So it's another valid lesson going forward. If we run it for a little bit, we should see that it's oh, sorry, I must have left something in by mistake. Let's jump over to another one. So one of the things we got working this evening was, for a blood vessel, if it has space around it, then creating a new immune cell. That process we need to sort out, because that's gone mental. But that took a long time to figure out how to find an empty space next to a blood vessel and produce a new immune cell that was next to it. So yeah, I haven't got a full model run to show yet. I think hopefully within an hour we might have fixed stuff and actually have something proper to show. But yeah, it's been, I think possibly with it more than we could shoot for a 2-day hackathon. It's been quite a big scope, this project, but I think we're almost there for getting something to run at least.
Great, thank you.
All right.
Do you want to do final thoughts by project, James, or do you want to go through all and maybe talk more as people continue to work?
I think we should let people to have their says. And I mean, if it's officially final, there's anything to say back. It's, of course, we could always join you and help you afterwards, but
Definitely.
Shall we? Is Max here, or is?
Well, I think
Yeah,
actually I
but
was
there's
going.
someone
We should,
needs to
let's do
leave.
let's do cell signaling next, because they're
Okay.
Yeah, we'll do actually cell signaling, and then zebrafish branching, and then we'll pick back up with Max after that, if that's okay, because those are the ones that have mentioned they need to go.
That's good.
Is it worth it, maybe just like if people have a major sensitive time commitment, even if they haven't said it yet, to put it in the chat now, and then we can organize kind of based off of priority?
Yeah, it's a good idea.
Let's do cell signaling next, so that we can decide who's the one after that.
Yes, thanks. That's great. We just have some other things on the schedule later today. So Megan, if you can share the screen. So we just ended our day with kind of making a very short presentation, just thinking about all the things that we did in this weekend, just having a little bit of a look back, think about what we did, what we all implemented, and how this fits in the bigger picture. I think you can do the slideshow. Yes. So we've been looking at signaling in this transition between phenotypes of cells, and we were with a group of quite diverse people from chemistry to physics to biology. So what we started off with today is this model where you have a layer of endothelial cells and they're going to change the phenotype. So we defined some cell types and we had an extracellular matrix at the bottom. And what we did yesterday is change phenotypes. And what we wanted to do is really focus on the signaling. So we came up with a very simple signal, which consisted out of 4 reactions. And we wanted to see how this changes the cell phenotype in response to the signal. And also made changes in the cell phenotype due to this signal, and then eventually also just have a little bit of review of the properties. So that's what we started off with today. So the model that we made, it's a multi-scale model with this transition with the signaling pathway in the background, and we wanted to use the antimony model to do this. And we made the cells adopt a new cell phenotype in response to the signaling and some kind of trigger based on the mechanical stress. And when they change the phenotype, they become more active and they become less adhesive. And eventually this leads to the degradation of the remodeling of the extracellular matrix. So these were all the steps that they wanted to implement. And in this weekend, we managed to think about a signal, which was a big step. We really had to think about biology and how to simplify this. But we managed to get a signal that we could implement. And we also have been playing with changing of phenotypes. So that's what we've been doing during this weekend. And there's still some things that we still need to do. So this is the model. And on the right, you see the simplified version that we took. So on the left, you see our simulation. And on the right, you see the signaling that we've implemented. So all the red cells, they have a signal, and the signal is increasing in time. I see that we didn't made a fixed legend. So the red cells are this value is increasing, but you don't really see this. But what's happening is that this cell is increasing, and when it changes a certain condition, then it's changing its phenotype. And we used the model on the right for that. So it's really still one cell responding based on the position, but we really want to extend this and make this more realistic. And as you can see, there are multiple cells, and when they become further into the extracellular matrix, they even change their phenotype even more. So I think next. So some things that we came across is that we tried to learn different techniques. So we used antimony modeling, also changes in phenotype. Just by trying and asking lots of questions. And one of the things that we really had to think about is to reduce the complexity of the signaling model. So we've been thinking about this a lot, talking about this a lot. How do you do this? How do you do this talking? And I think we're still in the process of implementing this. And I think as a group, and that's maybe most interesting to share with everyone, that we had a lot of group with a lot of people from different backgrounds. And how do you write down a problem in the simplest way possible without having this complexity? And in one of the last sessions, this is what James told us. So yeah, that's mainly the thing that we're also taking out of this workshop. Apart from learning how to use CompuCell, that it's also important to think about the biological formulation of your problem. So there are still some things that we would like to add to the model. So we want to have this trigger that's going to trigger the signal, and also this degradation of the extracellular matrix, but also improve some of the aspects in the model right now, because it's just been 2 days and we have just been trying a lot. So we're definitely thinking about reviewing some of the aspects and improving upon that. And then study the motion of the cells and this extracellular matrix and properties of the signaling pathway, and well, still open things to do. So that's just what we got out of the discussion at the end of the day, just reviewing on a really nice hackathon weekend.
Okay, well, we want to thank you for the effort and long time in August, late nights. So we appreciate it very much from you all.
Yeah, yeah, we all want to thank you for all your input, because it's been really informative for all of us.
And we're always here to try to help as you go forward.
Thanks.
Yeah, not just with this project either. If people have other ideas that they want to develop post-hackathon, we're happy to stay in touch about those as well. Doesn't have to be the project you worked on this weekend. So Liliana, I think, was the other one with tight time constraints. So if you'd like to go ahead.
Great, thank you. Yeah, so I was doing the model of zebrafish ray branching. So the first bit of the hackathon was really scoping, and did a lot of work on that, trying to figure out what scale, especially of this branching to model. You know, if I did the individual branching event, that would involve many different cell types and some dynamics that I wasn't even super familiar with. And as someone who's super new to CC3D, I wanted to make sure I was biting off something I could hopefully chew. So I ended up going with tackling branching, just scaling it down to one basically tower of cells, getting that to be stable, and then hopefully getting that to branch. So I'll share with what I have so far. So at the moment, I just have basically the tower of cells. This represents a skeletal array and a zebrafish tail, but right now it's just one cell width. So hopefully in the future, I think once I get this working, I would expand that out to a thicker width. But here we go with how it goes. So it's stable, it's not falling down, which was happening at first. But you can see that the mitosis isn't quite working. So I wanted this to grow upwards, and instead it gets stuck, and also has these super like energetic cells. The childs are in orange that divide all over the place. Some of my obstacles were first using links to make this ray stable. Me and Pedro developed this idea of using like basically a triangle of links that wants to be flat. So each of these cells, if I zoom in, actually has links with their neighbors as well as their nearest neighbors. So you can see here, there's actually more than one link here. So for example, this cell has 4 links. It has one here, and one here, and one here, and one here. What I was just working on was getting the child cells to have those same links. Was thinking that something in those links might have been leading to this kind of funky dividing dynamic that's happening up there. Another, I guess, tidbit that I learned and might be helpful was how to work with neighbors in Python particularly. And we were talking about how that would be a good thing to submit for more documentation, because there's a ton there. But I found that really helpful, honestly, to really get to know how the Python part of Cell Profiler, I mean, not Cell Profiler, CC3D, that's the other project I'm doing at the moment. How the Python side of the program can really be used to its full extent. So next steps is I'm really excited to continue working on this and to get this simple model branching and hopefully expand this to a slightly bigger, more realistic simulation. But yeah, this is what I've got so far. I made the colors kind of like flower, because at one point it was looking like a flower, like this was just exploding up here. And so yeah, huge thank you to everyone who helped me and everyone who put on this workshop. It was really well done, and I really appreciated the help this weekend.
Well, thank you, and we hope to continue to work with you and help you develop this.
Definitely. Thanks.
Okay, so does anybody else have a pressing time constraint? Or should we start going through the list?
I am at 3 a.m. right now, so if I can
Okay.
present.
Sure. Yeah, so from the wound healing group.
Yep. So to start off with, the goal was initially to at least have some match between the experimental time-lapse movies, which are shown for the wound healing epithelial migration, the scratch essays that have been published, with the CompuCell simulations. And there were a lot of ideas that we discussed in the first day, the first half of the first day, and the second half, the first half of the second day. And I didn't realize it at first, but it was a pretty big project, which obviously I could not do in a couple of days. So we, during the process of this wonderful hackathon, we narrowed it down to just getting it to work and getting it to look like actual cells, not something like lava lamps or not something like parachutes. At least that was a win for me. Yeah, I can go to the video. Just let me share the screen. Yep, so the thing that I managed to do was first to get the follower cells, which are the green colored cells, the leader cell, which are the red colored cells. And I added links in between to have some force, like spring-like mechanism. If I run this, of course, the leader cells are relatively bigger in size. So they have that phenotype going for them. And then in the last moment, just an hour ago or like 15 minutes ago, I added this small Mitosis plugin, because what I was seeing is that the whole, this green patch was moving ahead because there was no space for the cells to occupy. So I added this Mitosis plugin. And what you can see in this simulation is you see this nice, which people call as the actin ring or actin belt, something like that, in between two leader cells in this simulation. And the way I have implemented the force dynamics is just a very naive way of implementing it, is that if the cells in front of it have started moving and have started exerting some forces, then the neighboring cells behind them will also start moving with some small force. And that is what you can see in this simulation. I faced a lot of hiccups, and a big thank you to all those people who helped me. James, Gilberto, Pedro, Jim. Jim actually talked a lot regarding how do we do the processor, manage it on multiple processors. And one of the things is to understand the quirks of this software, to have it in terms of the proper syntax. So the follower, the leader, all have to be capital. Just some small things like that, which are very frustrating at first. But once you get the hang of it, you should be fine. Learned a lot of interesting things during the week and during the hackathon, especially once I got to play around for like 2 full days. Lastly, to conclude, the next thing is to add more biological details. As I was discussing, there is a lot of signaling as well that is going on. It's not just a simple force relay that is happening. There is a lot of biology that is occurring in these cells. And yeah, let's see if we can get it somewhere near to publishing it in the next few months or few weeks, hopefully. So, yep, that was it from my side.
That's really impressive. I don't think I've ever seen anybody get that level of detail with a linked tissue before. Really, really
Okay.
impressive that you could do that in 2 days.
Yeah, it was actually a lot of help from Gilberto and Pedro, and a lot of ideas going on in my mind and trying out a lot of things in a short span of time. I am actually surprised with myself, to be very honest. Thank you.
Yeah, it's always impressive what you can do when you have somebody else reserve 2 days for you to to work.
Yep, 100%.
But, well, great. Thank you, Roshan. So
Thank you.
then next, I guess we'll go back to Max.
Can you all see my screen?
Mhm.
Okay, let me load it in. Let me start from, oh wow, it crashed. Okay, I guess we can start here. So essentially, okay, essentially what we have here is two different strains of influenza virus. You have your red and blue. For the sake of this, we can call the blue our wild type and a red or variant. And what I wanted to model is how when both of these two types co-infect the same cell, how do they exchange segments and how does this produce these new recombinant viruses? And right here at the start, I froze a few steps in. Here you can see the green, which are your epithelial tissue cells, and then the purple is when infection happens. So here are variant virus infected the purple. And what I try to model is the spread of infection and how the reassortment changes as time progresses. My code is running really, really slow, so I'm going to set it to play and continue talking. Hopefully we can get some results. Otherwise, I took screenshots that I can share. And hopefully it started running again. Okay. Yeah, as these colors change, it indicates that it's entering the cell and getting infected. I'm actually going to change to a different Z layer here. Essentially, the obstacles I had for my model was one, developing this sort of like 2.5 D model where we have our X and Y dimensions, and then we have a Z layer that's really, really shallow. And the reason why I did that is I wanted one layer to be the tissue cells and one layer to be the infection, and that'll allow for the infection to spread better. And it's something I want to perfect as it goes on. It was something I really had trouble with at the start because I have a lot of cell components here. I have uninfected tissue, infected tissue, releasing tissue, and dead tissue, along with my two viral types and then my two internal viral types. And that leads to a lot of different contact energies. So I had to really play around with all the contact energies to make sure, hey, am I actually getting the cells to be infected? Once they get infected, are they moving around enough? And then once they get released, are they able to come in contact with uninfected and infected tissue and reinfect them? And sometimes even now it fails. So hopefully it doesn't here because I'm running really, really slow. But once I got it, it started working well and it moved to the reassortment side of things. Hopefully I get one of these cells to divide sometime soon and I can show you how it works. I can actually, in the meantime, pull up one of my screenshots. So what's this? So I think these go together here. So essentially what we had is that the two viruses infected the cell. You can see here on the y-axis is your level of reassortment. For some reason, the entire background was getting set to the blue 0, which is what I wanted my parental variant to be. So ignore any value lower than 1. 1 means that the cell was all from the blue variant. Every gene segment came from that. And 2 means every gene segment came from the other parent. And as you can see, as the virus began to divide and spread, it began to recombine and produce sort of new recombinant viruses. And right now I set the reassortment to be random. So it's a 50-50 scan. Essentially, it picks up a segment from one of the other ones. But as the cell grows in volume, sort of the stochastic fluctuations happen, and then hopefully I can pick up a pattern once I start imposing some of the constraints for reassortment. And that's sort of the goal for the future. My background is in influenza research and computational modeling, but I've never worked with CompuCell3D, and I really wanted to bridge those areas. In the past, I've studied how different hosts give different advantages to reassortment, and that allows them to serve as vessels to allow for pandemic strain evolution. I never got it tested in humans. Obviously, I can't go around infecting humans, but I hope to use this model for that and to sort of quantify some of my assumptions in the past. One thing my last paper uncovered was that it's the swine. If you guys remember the swine flu from 2009, it had a pig component, and that's why it was called a swine flu. And the reason why it includes a pig component is that swine are considered mixing vessels. And it was previously thought that the swine immune system would actually not target the viruses heavily. And as a result, a lot of this reassortment would happen, leading to new diverse viruses. However, our paper found that actually the swine immune system was pretty strong to it, stronger than the birds were. But in fact, the spatial compartmentalization of the swine's lung allowed for genotypes that were unfit for the pig, but more fit for humans to sort of prosper in those localized environments. And perhaps with CompuCell3D, I can actually model it, quantify it, and see it in action. So I think there's endless possibilities I can explore with this model, and I hope in the future I get the chance to do so. I don't know if there's any other questions on a PowerPoint slide I forgot to tackle. That's what the model was for the most part.
No, I think you about covered it. Looks good. Definitely a lot of progress between yesterday and today too. So
yeah, there's a lot of progress, and I think your model is ready to be explored in the next level.
Yeah, I hope to get the opportunity to do it entering my senior year of undergrad, and hopefully I can spend some time working on it and exploring different routes.
great.
That's a very complex problem, and getting it up in 2 days is impressive.
Thank you.
All right, so we'll go on to maybe calcium zebrafish next.
Yeah, so I will try to answer the question. So our goals for today were to implement the calcium diffusion in this first cell division. So yeah, that were our main goal, but we couldn't reach that goal. What we reached was to make the ER that this compartment grows to the time, and basically yeah, when we reached that part, you already saw that video, or probably we can share again the simulation that we got for that growing compartment. And but we got some errors when we tried to implement the diffusion. So yeah, we were working on that part, and we really want to at least implement a single or simple version of this diffusion after everyone basically presented their results, because yeah, we got some errors and we couldn't figure out how to solve that part. So yeah, so I think that's everything that I want to say right now. So could you share the yeah, I just, or Dulika, which she's next to me, she will share the screen just to show you again the simulation we got. And yeah,
This is the working one.
yeah, so this is the part
previous one that we
yeah, so this is the part that we basically
previously did.
yeah, just show you in the previous session. But yeah, trying to implement the diffusion in this, or even trying alone to implement the diffusion, we couldn't basically implement something. We got some errors.
Yes. So we have been playing around in this part. Where is it? XML? Yes, here.
Could you talk?
Yes, we have been playing around with this part of the code, and we are constantly getting a kind of an error, but I'm not able to make out where the error is from. So I'm opening this in the first step. Yeah, it closes initially and then it gives an error the second time.
So yeah, but
So I'm guessing this is a very big error because it is actually giving us an unknown cell type ER and Cyto.
Okay, go to the beginning of the simulation. We should probably debug afterwards because we want to get everybody through, but let's you've defined the cell types there. Okay. Scroll down to the don't keep going. Keep going. Oh, that's easy.
No.
I think the problem is line 95.
95.
Here. Okay.
Comment out line 95.
Right. I think the same line was here as well, so I commented this out.
Oh, fine.
Okay.
Yeah, so try
So we
running
should
it.
try running it. And then we should move on to make sure everybody gets to talk before it turns people at India at 3 a.m. already. We're very grateful to you for sticking around.
Yes.
But let's try it, run it and see what happens.
Okay.
You have to save.
Oh. Yes. Oh, yeah, okay. Now there. Yeah. Oh. Yeah, this is not.
Okay, so
Right, let me turn to calcium, stop, and then do first step. Yeah, it's all throughout.
Fine. So we'll work on that together afterwards. But
yeah,
but
okay.
the syntax error was that when you make a list, you don't put the list in quotation marks.
Okay.
Okay.
Okay. Okay.
Yeah,
Yeah,
thank you so
it
much.
reads that as a single string, so it thinks that's a single variable that you haven't defined.
Okay.
Okay, yeah, thank you.
I could be wrong. I think though that I think I've seen that pop up twice now today. Does CC3D initialize with it in quotation marks, or were people just pulling from the same chunk of code? It's also possible, I guess, that maybe both just did it.
Well, there's certainly possible that the code snippets have a typo in. But I've never seen that error before.
Okay.
Doesn't mean it's not in the code snippets, but I've just never seen it before.
It may have just popped up twice.
Remembering there's always this problem. You have Python, you have XML syntax, you have antimony syntax. And so you have to keep track of a lot of different languages, and they have different rules. And so here, the XML, for example, when you have lists in XML, you're not allowed to have spaces after the commas, which is strange. But it's those are rules that are not CompuCell rules. They're imposed by the XML formats. So, great. Okay. Good. Well, I'm glad it ran at least now, even if it's not doing what you want. At least it runs. That's a start. Okay. Who else do we have still? People
Thank
have been
you.
very patient.
Yep. So we have cell elongation, OV cancer, and circadian clock. Does anybody from that group have a time constraint they need to go? Because if not, we'll just go with cell elongation. All right, so Izzy, we'll just go ahead and go with you next then.
Okay, sweet. So this is the video I showed everyone yesterday, I think it was. So this is what I'm trying to model. So it's my cell stretching out, and then it comes and clumps back up and then stretches out again. And have been able to show that elongation. And it is coming back together. And then it's taking its time, will stretch back out again. So what I've added today is the green part is the lampopodia, and this gray part is the rear edge of the cell, so leading and following edges of the cell. And these are using links. So there's a link between the leading edge and the center of mass of the cell, the rear edge and the center of mass of the cell, and the leading and rear edges. So this just is helping to align those with the elongation. It's a little bit buggy at the moment, so we just need to work on getting the target length for the link just right, so that these are actually sitting on the leading and the rear edges. But yeah, and then following that, I want to introduce the actin network for the leading edge, so it is controlling some directed migration for these. Yeah, if anyone has any questions, please go ahead.
I think you are very I forgot the word. Courageous to approach elongation in CompuCell.
Ambitious is the word you're looking for.
Ambitious, yes, very ambitious. So congratulations, I think.
Thank you.
What was the signal most? I mean, there are a lot of things that have been frustrating or difficult, but what would you say were the biggest obstacles to getting this to work?
I think playing with the contact energies because it's such, like, it's just playing around with them and you're fine tuning so many different parameters that it just takes a while to actually figure out what's having the biggest impact.
That makes sense. I mean, one thing I do a lot with that kind of thing is I'll edit the in the property editor on the left. I'll type the values in by hand and change them. The one problem with that is they're not logged. So you type in the values and you end the simulation, you don't know what you did. And we've been working recently on just adding a logger so that whenever you type something into that editor, it saves the values and the times, which should be simple, but it winds up being slightly less simple than one would like. But I think one of the newer CompuCell releases will keep track of that, so that if you're playing, it will keep track of how you change the simulation. So if you get something you like, you'll have it there. So you don't have to keep going back to the source code and changing the model and then rerunning it.
Yeah, that'd be
So that
really
might
good.
speed up the parameter exploration a little bit. But that's great. Well, thank you. That's good. Great. I hope it's useful. I'd love to see this collective simulation work. I think you've got the pieces really.
Yeah, definitely. We'll just have to, I think one thing that might be challenging is that my stem cells won't have the leading and following edges. So it will be enabling division from a cell with no compartments to then initializing compartments when it does divide.
I have a hint on that. Julia may have better ways of doing it. I would create the compartments from the beginning, but in the stem cell have the compartments all have identical properties.
Oh, yeah.
So that they're there, but they're not doing anything, so they don't show up.
Yeah. Okay. Yeah.
And then after you divide and you change the type, then you give them their different properties. And then you don't have to instantiate new compartments. You're just taking hidden compartments and making them active.
Yeah, no, I think that's
that's
something
actually
that
how I
we
would
can
do it as well. Yeah, that's about my approach.
Okay, sweet. Thank you.
Pedro, did you have a comment?
Yes. So basically, the parameter juggling with the contact energies is really tough. I agree. And TJ developed a demo of a optimization process to find best energies to in order to lower a predefined cost function. So this demo, I don't know if you have the demo.
Me?
Yeah.
I don't think so.
I think the demo is on GitHub. I can send you the link then.
Oh,
And
awesome.
I couldn't run in my CC3D. I don't know what's the problem. Seems to be a syntax issue from a previous version. I'm not sure, but I will give you the link and you test. It's basically a chemotaxis simulation, and the program, the optimization function finds the best, I think the best lambda chemotaxis to make the cell move at a certain velocity, certain speed.
Oh, okay. Yeah.
So that's basically the optimization in the demo. It's very, very simple, but the code is not so small, so it will take a while to decipher everything. Decipher? I don't remember the word.
Yeah. No, that'd be cool. I'll take a look at that.
Yes, decipher. So yes, I will try running my PC again, try debugging if it's still bugged. And I will send you the link. We can talk again later about it if you want.
Cool. Thank you.
All right, thank you, C. So I think next we'll do ovarian cancer.
Awesome. Okay. Actually, I'll screen share and Yep. So let me start from maybe the biological side of my experiments. So in the experiments which I have done, I have basically induced senescent in some of my mesothelial cells. And as you can see in 2D, the senescent cells look much bigger in size. So this is something which we thought of introducing in our model. And then just to confirm that, I've also done S-beta gal staining, which is one way you check for senescence. And in my control compared to my senescent side, you can see that there is more stain, plus again, that the cells are more wider and broader. So now to get some ideas about the speeds which we wanted to implement into our models, we basically looked at non-senescent cells moving. I hope you can see the move. Can you see the move? And is the frame rate okay? All right, awesome. So, yep, this should be fine. And then our senescent cells move. Although, pardon me for the different confluency, it should be similar to compare, but what we figured that while individually looking together at certain cells, which were senescent, that they're more elastic, they're squeezing between places and going around. Although couldn't really figure out much differences within their speeds. So we decided to have their speeds similar in our model. Then we looked at some ways in which how cancer cells kill these senescent cells. So one of the way was, which seemed like signaling. So if you look at this senescent cell, it just undergoes some sort of apoptosis event. If you want me to replay it, I can play it once more. Yeah, while the other one, which looked very mechanical, was this chipping off. Well, as of now, we have only reached to the mechanical part. We thought of doing this, but yeah, I believe it was kind of hard in 2 days to implement all that. So I can show you where we started with. So in our modeling, we basically started with this model with just 2 cells having no, oops, it's moving very weirdly. But basically just 2 cells having the different sizes and no forces at all, and seeing how they spread and stuff. That's it. And varied contact energies. Then we moved on to add some forces to it. I'm not sure why this is moving weird. I'll just move the slider on my own. So when we added forces, they mimicked more of an environment which we were seeing, and it's random. So yeah, it's basically in all directions. Then we made non-senescent cells divide and cover the places. Oops. Wait, not this one. My bad. This video here, if you can see it. So this is so this was our initial layout. We decided on an initial layout. I'll come back to that in the slides. And then we made them sort around if there is some sort of sorting happening, then made them divide and fill up the space and become a confluent. Senescent, non-senescent monolayer. Then we added cancer cells to it. Well, here senescent cells should be blue, but we implemented it like that. So yeah, just remember that these are senescent cells. Then we implemented the other code, wherein now when we have a confluent monolayer, so starting with the senescent and non-senescent, introduced cancer cells, introduced their proliferation, and then with time we see that as they grow, they basically take the senescent cells first, and then the non-senescent cells. It should be visible in some time. You can speed it up. Yeah. So senescent cells are the ones which even here at far distances will disappear first, and then cancer cells basically start covering the non-senescent. One thing to think about is that if you see that the division is happening in a very synchronous order for cancer cells, which is not something which you observe. So we were thinking of making some of them out of phase. to have a more gradual decrease in the number, which we haven't implemented yet. I'll come back to my slides. So a lot of inputs for this. Actually, Pedro helped us decide on the two layouts. We decided on the left one because this restricted our degree of freedom to 1. And we did not want only 2 cells to be, having the mechanics. And then basically the last final model was this. We reached the confluency, and these are the pressures getting stabilized, and the exact ratio which we observe in my experimental setting. So when you have single cells, less subconfluent condition, you have the ratio to be around 3.5-ish. And then when they become confluent, it becomes 2.5. This is what we observed in experiments too. So we were able to implement that. And then now we bring in cancer cells, and we have the chemokine field here, which senescent cells are secreting. We let them sort, although there is not much difference here because the amount we left them for sorting after chemotaxis was around 300 MCS, which is probably not enough. But you can see some differences, like this cell here has migrated towards senescent cell and similar stuff. And since cancer cells are uptaking the chemokines, you see the reduction in the in the chemical field too. Then we showed this, which basically shows that, all the senescent cells are gone, cancer cells have cleared them off, and you have nothing left because there are no chemokines being secreted and the decay is high. And then again, with time, you get your non-senescent cells also getting cleared off. It was a super nice experience for me. It was my first time actually downloading CompuCell3D on my PC right before the workshop. My two teammates, which Lakshay and Uday, they also downloaded it actually in the middle of the workshop. And we're really, really, really grateful for this amazing experience. It was super fun. And we're planning to work together on this and try to make it a better experience. Haven't thought far enough to publish it and stuff, but I might think of him adding this part, or maybe something of a 3D model to my experimental side, and then, taking it from. That's all. I would love to hear our progress and whatever feedback. And thank you everyone who contributed to it as much as we did. Thank you.
Well, again, it's incredible progress, and I think we've got the foundation for something really impressive that can be validated against experiment. So I think the steps to go from here to a really predictive model of the experiment aren't so many.
Yeah, that makes sense. It feels like you have kind of crossed the hard step. Yeah, if any of my teammates have any comments, please go on. I'm sorry I did not, mention that. Go on, Lakshay.
No, I was just going to say this was a really cool opportunity. Like personally, I'm more into evolution biology, and that's what I'll be starting my master's in. But then I've worked in cancer before, so it was just an exploratory sort of thing for me. And CompuCell is one of my favorite tools right now. I just got to say, it's really cool. Yeah, it was an amazing opportunity.
Can we use that as a soundbite in future advertising videos?
Yeah, you most definitely can. If you need a video as well, I'm down for the testimonial. Yeah.
Great.
Oh, we definitely could. That would be kind of.
So the tuberculosis model guys actually had something that they managed to get fixed in the last half hour if they wanted to reshare their video. If James, if you're still around.
Is there anyone else who hasn't presented, I guess, first?
No, we did lose Daniel for the circadian clock project. Oh yeah, we were going to ask if Jim, I know, spent some time with him. Jim, did you want to maybe say a quick something or other about how the circadian clock project ended up?
He made a lot of projects. He basically got the circadians to cycle in CompuCell in the Tellurium model. He's also got his cells laid out in a slice of a lobule. What he needs to do now is kind of couple those two together. So he made some progress and he's getting there, but he hasn't quite got the cells in the simulation to simulate, to synchronize, but he's getting there.
Good, thanks.
And I guess I could say something in the I know the follicle we had to leave as well, and I helped a little bit, and she has now the antimony population model running, and so now the issue is using that to do the cellularization process and add those rates to her base model of the follicle signal. So I think that model is in pretty good shape for development too.
Great.
So
yeah,
if anybody wants to show anything else, you said that the TB group has a new video to show.
yeah, it sounds like they fixed a critical bug and now have a now their simulation is ready to show. So.
Yeah, TB or not TB. Finally, we have TB. So yeah, let's see if we can show it.
I think that's the first time everybody's ever said that with a happy tone.
That's very true. So this is far from perfect, by the way, but I think we've got enough of the key processes going now that we've got something to show here. So what we can see at this point, I've let this run just for a few steps, is we have a sort of uniform set of blood vessels initially, which are, if we zoom in, are the blue pixels, and in the center we've got the bacteria, and the purple ones is there's some resting macrophages that we initialize in the model, and here we can also see that they're starting to get recruited from the blood vessels as well with a certain probability. And then in terms of the bacteria, when these resting macrophages come into contact with the bacteria, they become infected. I also saw, it was a few time steps back, possibly I could let it run in a second, some of the bacteria were changing state from slow growing to fast growing in response to the oxygen. We've also tested earlier on that the infected macrophages can get more infected as they sort of count the bacteria that they come into contact with. And then the extracellular bacterium cell is deleted, and it's kept track of in an internal counter within the macrophage. I mean, this is an unrealistic growth rate for the bacteria, but it was just to see if we could get some of the key behaviors shown here. In terms of the oxygen, we can see that the oxygen fields are developing nicely. And now that it's run long enough that there are some infected macrophages, you can also see that they are now starting to secrete chemokines as well, which is start to recruit some more of the macrophages as well. So this is still haven't got all the processes in place. But if I run this a little bit now, we might see some of the things just evolving a little bit. It's a very slow running model, I should know. But yeah, we can see that dark green is where a slow growing bacterium has become fast growing as it's near a blood vessel. It's then been absorbed by this infected macrophage. So yeah, we can start to see some of these processes are now starting to take shape. In terms of T cell recruitment, we still haven't quite got that in yet, but it shouldn't be a difficult thing to add. And we also want to add the ability that cells die and become caseum, and this sort of necrotic dead cell type that will help stifle the movement a bit of other cells, as it's a frozen cell type. So I think in terms of most of the key processes, now most of them have been added. So it's mainly just going to be fine-tuning the parameters to get this working more or less as we hoped. So yeah, especially given that it didn't run earlier, I was sort of fixing this over the last half hour, so we would have something to show. So yeah, I think we're almost at the point that we wanted to be at the start of this weekend. So yeah, in fairly good shape, I'd say.
Congratulations for that one.
Thanks, Pedro. Yeah, really appreciate your help on this as well.
Okay, well, I think that everybody is presented. I think that's wonderful. I could certainly stick around for another hour to help people out. I'm sure people are tired. Maybe one or two of the other instructors can help people out if you like.
Yeah, I'll stay here for support as well, for finding links and resources and stuff.
And with that, I want to thank you all for being brave and sticking out 8 grueling long days. And I look forward to seeing these projects develop and working with you going forward. And thank you to all the instructors for the incredible amount of effort you put in. And so that will conclude the official part. I'll turn off the recording, and people who would like to continue to work, I'll leave the Zoom running for the breakout groups, and I'll be happy to join people and work with them individually.
And there is a last obligatory activity, which is sending good vibe messages for TJ today.
Yes, I don't know. Has he named his son yet?
No, I haven't heard.
You have to give a cell type name to the.
Name his son CompuCell.
Well,
CC.
Oh, there you go.
We did have somebody many years ago.
CompuCell3D.
We did have a group member many years ago who went. We went out at a conference. They went out drinking after the conference dinner, and they came back with a huge Python tattoo. That is the Python logo for the software. Huge, because of Python and CompuCell. So I don't know whether that was regretted afterwards or not, but he's spending the rest of his life with a huge Python logo. He didn't have the CompuCell logo. By the way, the CompuCell logo itself was developed by a student. One year we had an in-person meeting, and we had a little competition for the logo because we didn't have a logo. The competition was a bottle of wine, and the students all submitted logo ideas. And so the little CompuCell logo was a student hackathon creation.
Yeah, so it's very meta. The CompuCell logo was generated in CompuCell.